Hey guys. All right, so this is going to be the video walkthrough, PowerPoint walkthrough for the second section of um, chapter 11. And um, we're going to be talking about specifically the learning objectives 2, 3, and 4 of chapter 11, which is defining the main effect for one factor um, and the interactions between factors and how to identify them from a two-factor design. We'll talk about more complicated, like three-factor and other designs. We'll talk about that in other sections, but this for now, we're going to just talk about the two. Explaining how interactions can influence interpretation of main effects, and then describing and explaining um, independent the independent relationship between main effects and interactions. So that's the three objectives for this section. Um, Remember from talking about in the first section, we talked about the primary advantage of a sorry, I'm losing my voice, of a factorial design is that it allows us to examine how the unique combinations of factors or independent variables acting together can influence behavior, right? Because that's more how variables behave in the wild, as the guy that does your JASP videos talks about. Because in an experimental setting, when we're only looking at a small number of variables, or how one variable affects another variable, and a lot of times in real life, it is a different situation, right? There's multiple variables affecting each other, which are then affecting the dependent variable and all that. And so factorial designs give us the ability to examine that experimentally and statistically, right? And so the first simplest design we're going to discuss to help you guys understand the whole concept of factorial design and specifically main effects and interactions is a two-factor design. Remember, factor is synonymous with independent or quasi-independent variable, right? So when we say two-factor, we're saying there's two independent variables that we're looking at and one dependent variable, right? So um, the two-factor design can be represented by matrix, which matrix is a fancy word for a, a spreadsheet, a chart that we've looked at many times, and we looked at in the last video as well, where there were four cells, right? There was two columns and two rows, four cells total, and each of those cells corresponds to a separate treatment condition, right? And so to remind you guys, here's table 11.2. This is talking about, remember that experiment we talked about where they were looking at the effectiveness of studying, specifically the dependent variable is exam scores, but studying whether they're studying on paper or on screen, so the method of studying, and then um, how the time of studying was controlled, whether it was a fixed set time by the researcher or whether they were self-regulated, where they could just decide when they were done studying, when they had a grasp on the material. Um, and so you can see those two variables in the columns and the rows here. And you can see our four cells are the mean of 22, of 18, and then of 18 and 14. So those means, those are our cells that we're talking about. And you can see how each one is a combination condition, right? So this one is on paper. They studied on paper for a fixed time. All right, that's cell number one. This cell, they studied on screen for a fixed time. And then this one, they studied on paper for a self-regulated time. And then here, they studied on screen for a self-regulated time. Okay, so there's four combinations, four conditions there that are distinct, right? They're different from each other. And so the data in a two-factor design provides three separate and distinct sets of information, which is describing how the two factors affect the dependent variable independently, how they affect the behavior independently. So how factor A affects behavior or the dependent variable, how factor B affects. Those two things we're going to learn are called main effects. And then also how they jointly together affect behavior. So that's going to be known as an interaction, which again, we will talk about more in a second. But that's the three sets of information you're going to learn from a simple two-factor design. So, okay, let me make sure. Yes, okay. So for main effects, I'll pull this up so you can see it more in a second, but the mean differences among the levels of one factor is a main effect. So for each independent variable. So a two-factor study would have two main effects because there's two independent variables, right? There would be an independent, there's going to be the potential for a main effect for the type of studying they did either on paper or on screen, the mode of studying, and then there could be a main effect for the control of time, whether it was a fixed time or a self-regulated time. So there could potentially be a main effect for each. There's two possible main effects because there are two independent variables here, right? This data set, this is the same. It's just showing you the means for the columns and the rows. This is the same chart we were just looking at, but this data set is showing you this was structured to show you that there could be main effects for both factors, for both independent variables, but no interaction between the two. So that's what this is an example of. So you find the main effect for, or you can see the main effect for the variables by looking at the column or row means. So if you look here, for the columns, the on paper mean was 20 overall across conditions. Total on paper was 20. The mean, which again they're just averaging the two numbers above them, for on screen, the whole on screen condition was 16. So you can see there was a difference here of 4. So there was a difference. They were not the same. There was some sort of effect happening, right? And then over here in the rows, you can see that for fixed time, the mean was 20, and for self-regulated time, the mean was 16. So again, there is a difference here. There is something happening. There is an effect. Now, of course, you still have to evaluate these statistically, right? There still has to be a hypothesis test, a statistical significance test to determine if that difference of 4 points is for the on paper and on screen, is that statistically significant? Is the 4-point difference between is the 4-point difference between the fixed time and self-regulated time, is that statistically significant? Yes, there's a difference, but you have to actually do a statistical test to determine if it's statistically significant. But overall, you can see how you can tell if there was an effect. Obviously, if these two means were the same, then there would not be an effect here, right? And so for this, you could say that fixing the time that they studied, controlling having a set time that they studied, that increased the test scores by an average of 4 points, right? Because when they were self-regulated, they were on average 4 points, they scored 4 points lower than when they had a fixed time, right? Okay, and then same thing, you could say down here, when they studied on paper, they scored on average 4 points higher than when they studied on screen, okay? So that's two separate main effects, main effect for factor A and main effect for factor B, right? Now, what is the interaction? What about the interaction? So, if one variable or factor has a direct influence on the other, or on the effect of the other, so if study time affected their exam scores in terms of how it affect, or well, let me back that up. If study time, the control of study time, if that influenced whether the paper or screen affected their exam scores, you see there's a multi-level thing of effects happening. When you have to say something like that, when one independent variable influences the other, um, then that is what is considered an interaction. The most common example that you guys are probably aware of is drug interactions. So there may be two different drugs that you're looking at the effects of on behavior or on, depression or whatever it is. And one drug may affect the efficacy of the other drug, right? Maybe taking one drug with the other drug exaggerates the effects of the other, or maybe one drug minimizes or completely blocks the effects of the other, and makes it so that it's not even able to work, to improve or change behavior. And so when that happens, that's considered an interaction, right? And so um, if the if the two drugs or the two independent variables or the two factors are independent, there's no interaction. But if there is a dependent relationship, which we will talk about in a second, then there is. So this data set is actually what came from the actual study. And this is is showing how there is an interaction here. So you can see that the main effects are the same here. They didn't change. So the mean, well, actually, let me go back here so that I can show you, I can actually highlight it better. Okay, so you can see that the mean here, the column means and the row means did not change overall. So the main effects are still there. There's still a 4-point difference between paper and screen. There's still a 4-point difference between fixed time and regulated, self-regulated. So the main effects are still there. There's a main effect for factor A, there's a main effect for factor B. But if you look at these individual cells here, they are actually different, and that is showing you an interaction because, or well, let me back up. If your mean differences, like your column and your row mean differences, cannot be completely explained by the main effects, then you have an interaction. So what do I mean by that? Well, if you see there's 4-point difference here and there's a 4-point difference here, but if you look inside these cells, fixed time and on screen here are exactly the same. There's not a 4-point difference there. They're exactly the same. And if you go from self-regulated to, or I mean, if you look at the self-regulated, there is a difference, right? And then same, if you look on paper, fixed time and self-regulated, that didn't change. And that's supposed to go down, but it didn't. And here it did go down, of course. But so the trend, the direction of which it's going down or up or not changing should match these overall means. If it doesn't, then there's some sort of interaction happening. Okay, so let's go back to the slides. So this is what I was talking about, the dependent relationship, and also another way to view these is the a graph. So we've been looking at these matrices or these tables, but there's also, you can look at graphs. So you can say that one interaction exists, or that an interaction exists when one factor or independent variable is affecting the other. But you can also say when the effects of one is dependent upon the levels of the other. Remember that depends word. It depends. When you see that, that should be a red flag that there is an interaction involved. So if we go back to our example here, the difference between paper and on-screen conditions, the difference between studying on paper and studying on a screen in exam scores, that depends on how the study time is controlled, right? So, yes, there can be a difference between studying on paper and studying on screen, but it depends on whether it is a fixed time or a self-regulated time, right? Because when it was self-regulated, there was a difference. But when it was a fixed time, it didn't matter if they studied on paper or on screen. They scored the same. So let me check my notes real quick and make sure that I'm touching everything here. Yes, okay. And so you could say it the other way too, that between fixed time and self-regulated time, the effects of having a fixed time or studying in a self-regulated time depends on whether you're studying on paper or on screen. Because if you're studying on paper, it didn't make a difference if you studied for a fixed time or self-regulated time. But when you studied on a screen, it did make a difference if it was fixed time or self-regulated. Okay. Whereas if we went back to the 11.2 table or matrix, you can see that they don't depend on each other, right? Like the difference is the same. So, the difference is, so we see 22 to 18, that matches the trend of it going down, right? Here, 18 to 14, again, that matches the trend of the on-screen being less. Over here, 20 to 16, so that means it should go down when we go from fixed time to self-regulated time, and it does. And if we go from fixed time to self-regulated time, it goes down, and it does. So it follows the same trend. So the fixed time and self-regulated time, the variable the effects on exam scores does not depend on the paper or the screen method, and vice versa. They don't depend on each other because the difference is the same there. It follows that trend, right? And as a reminder down here, just to remind you real quick before I forget, that a statistical test is needed to determine if the interaction is significant. We already talked about that a second ago, but again, if it looks like there's a main effect or it looks like there's an interaction, of course that has to be evaluated by a hypothesis test or a statistical test before we can say with certainty that it is due to, that it is a statistically significant result, that you can put stock in it, that it's not due to just chance or error or something like that. So now we need to talk about the graphs. So when the results of a two-factor study are graphed, non-parallel lines indicate an interaction. Well, what in the world does that mean? So we're going to go to the slide and I'll show you. So this line graph lines up with this table 11.2 where there was no interaction, where there were main effects but no interaction. So you can see the fixed time line is the top line and the self-regulated time is the bottom line. So you can see that fixed time was higher than self-regulated time. So the scores you can see on the y axis, those are the exam scores, the mean exam scores. So on average, studying for a fixed time led to higher exam scores than the self-regulated time because that line is above the self-regulated, right? Now, if you look on the x-axis, the paper and the screen conditions, you can see that the you can see by those the data points. Sorry, that those data points represent those four conditions, right? So paper is the paper condition for fixed time and self-regulated time are those two dots. And then screen, if you go up those two dots, that's for fixed time and self-regulated time. So those four dots represent the numbers from those four matrices, or those four cells in your matrix. And then again, looking at the difference between paper and screen, you can see that the dots for paper, those two dots are higher than the two dots in general for screen. And so you can see again that the trend goes down, right? Those lines are going downward. So paper led to higher exam scores than studying on screen. But again, because those lines are parallel, there is no interaction. Now, this is a line graph that represents the 11.3 table. Let me get there real quick. Which did have an interaction, remember, because these cell means right here were different. So you can see that they are no longer parallel. They are actually crossing or heading towards each other. They are not parallel. And so when that happens, that indicates that there is an interaction occurring. And so, again, you can see for paper, the paper condition, the fixed time and the self-regulated time, the conditions were the same, that the exam scores were 20 no matter what, right? There's no longer four dots there, there's only three, because those numbers were the same. They're in the same spot, they're at 20. And so that's how you know that there is an interaction occurring in this data set, which we will talk about that more in another graph in just a second. So we talked a little bit just now about how to identify this interaction, but specifically, how do you observe it or identify it when you're looking at that matrix, at those tables that we were talking about? So you're comparing the mean differences in any individual row with the mean differences in the other rows. And again, same with the columns, which we kind of already talked about, but we're going to break this down again just to kind of make sure you guys have it. So the size and the direction of the differences in one row are the same as the differences in the other row. That means there's no interaction. So if we go back to, we keep going back and forth, I know, but the 11.2 table, if you compare, or if you subtract 22 with 18, you get 4. If you subtract 14 from 18, you get 4. So those are the same. And same for the columns. And well, those are the columns. Same for the rows. If you subtract 18 from 22, you get 4. 18 from 14, you get 4. So if you get the same number across rows or across columns, then you know there's no interaction. Okay. And the direction has to be the same too, right? We talked about that before. The differences, if the differences change from one row to another or one column to another, then that's evidence of an interaction. So we go back to 11.3 and we look at 20 minus 20 is 0. Okay, but 20 minus 12 is 18. Okay, well, hold on. If they're different, that indicates there's an interaction. And then again, if we wanted to compare the rows, we would say, well, 20 minus 20 is 0. And then if we did 20 minus 12, well, I moved it, that's 8. Well, 0 and 8 don't match, right? And so because those are different, you know that there is some sort of interaction happening. Now, again, remember, we've said this several times, but a statistical test is necessary to determine whether this interaction is significant. So we see that there's some kind of interaction happening, but we have to use statistics to determine how significant that really is. Because there could be a small difference, but if it's not enough to be considered statistically significant, that means it's probably likely due to error, or maybe too large of a sample size, too small of a sample size, or it could be due to inaccurate data collection or bias or some kind of confounding variable, things like that. And so, or it could just be due to chance. And so when looking at main effects and interactions, you have to make sure that you're using that statistical significant analysis test to determine determine how strong that difference is. Okay, sorry, my iPad was doing something weird and I got distracted for a second. Okay, so how do we interpret this? So significant effects indicated by statistical analysis. Oh, wait, hold on. Before we get there, I did want to say any differences that we were just talking about need to be evaluated by that hypothesis test. If you're wondering, if you want more information about that, or if I kind of like threw you off by saying all that, go back and look at box 7.1 in your textbook. Obviously that's in chapter 7 since it's 7.1. That will help you remember exactly what we're talking about and why we're saying that it needs to be evaluated by a hypothesis test and looking for that statistical significance. So you have to be careful about interpreting differences for interactions or main effects without a statistical test. But even if you have a statistical test and it is significant, that's what this first point is saying, you still need to be careful about how you interpret the outcome. Because main effects may present a distorted view of the relationship between the actual variables. Because each main effect is an average, it may not be an accurate representation of the individual effects that were happening, again, because of an interaction, right? And so you need to be careful about saying this variable is affecting this variable definitively, especially if there's an interaction, because it may not be that simple. So let's look at figure 11.4. I can't remember how many pages over it is. Here it is. So this example is showing you the relationship between the TV viewing habits of 5-year-old children and their future high school grades. Okay, so there's two variables here. There's whether they watched, the type of program they watched, educational or non-educational, okay, and how much TV they watched as a 5-year-old, whether it was a small amount or a large amount, okay, and then the dependent variable is their high school GPA, okay. So if you look at the matrix over here, you can see, I can't highlight it, but you can see that the educational programming, well, let me back up. There is a main effect for the type of program they watched, okay? By looking at this, you can see, and why? Because if you look at the means for the rows, you see that educational had a mean of 83 and non-educational had an overall mean of 71. And so there's a large difference there. So there was a main effect for the type of programming they watched. Specifically, it looks like, and you can see this from this graph as well, that it looks like educational programming led to higher GPAs than non-educational programming. Again, because the mean was 83 and the other one was 71, but also if you look at the graph, the educational line is higher than the non-educational line, right? So that would lead you to believe that watching educational programming as a 5-year-old leads to higher GPAs. But obviously, you know where we're going with this because it's an interaction. It's not going to be that simple. Now, if you look, let's talk about the other variable, the second variable, the amount of TV they watched. Well, if you look, the small amount column mean is 77 and the large amount column mean is 77. Well, they're the same. So there was not a main effect for small amount and large amount. So the amount of TV watched seems to not have an effect on their high school GPA as far as how much TV they watched when they were 5. But if you look at the graph, you obviously see that they are heading towards each other. So they are not parallel. So there is an interaction. And so you can also look at the matrix and see that the size of the difference between the cells, remember the size and direction of the differences of the cells, does not match the overall means and is not consistent from column to column or from row to row. And so because of that, there's an interaction as well. So what does that mean for these results? So that's what this means about being careful how you interpret main effects. So you see this main effect for education versus non-educational programming, and you say, well, watching more educational programming as a 5-year-old, it's going to lead to higher GPAs. But that is not completely accurate. It's also not accurate to say that the amount of TV a child watches as a 5-year-old does not affect their high school GPA, because there was no main effect for that. That is not accurate either, because one of those variables depends on the other. So you would say you could say there was no main effect for the amount of TV that the children watched as 5-year-olds on their high school GPA, unless you look at, or it depends on the type of programming that they watched. So yes, there was no main effect, but when you compare educational to non-educational, there is a difference, because it depends on the type of programming. So if they were watching educational programming, then watching a large amount of TV meant that they had a lot higher GPA, and vice versa. If they watched non-educational programming for a large amount of time, it was a lower GPA. Now, if they just watched a small amount of TV as a 5-year-old, it didn't really make a difference whether it was educational or non-educational programming. If they watched a small amount of it, it didn't really increase their high school GPA. So if we wanted to say what's the best way to increase their high school GPA according to these variables and these results, it would be that if they're going to watch a large amount of TV as a 5-year-old, it should definitely be educational and not non-educational, right? And so, but this just shows you, one, how to interpret these things, but also how to be careful of main effects and non-main effects. If there's an interaction involved, it's not as simple as saying there's no main effect or there's a main effect. That's why most of the time an interaction is reported first in a journal article, and then they discuss the main effects. But the interaction is usually what has more of an impact and what sheds more light on the actual relationship more than anything else. Okay, so let's see. Okay, so again, this is kind of reviewing what we were just talking about. What we talked about at the very beginning. There's 3 separate sets of mean differences, 3 separate sets of information that you learn from a factorial design, from a 2-factor factorial design. There's going to be a mean difference for factor A, or a main effect. There's going to be a mean difference for the main effect of factor B, and then there's going to be the mean difference for the interaction between A and B. Okay, so again, those 3 separate pieces of information. Let me go to figure 11.5, and this right here is showing you those 3 things that I just talked about. And then if you scroll down, this figure is a great thing to show you how there's the first one, part A, is showing you a main effect for factor A for those rows, but there's no main effect for the columns for factor B, and there's no interaction. You see the two lines are parallel. The second middle set there is showing you that there's a main effect for both factor A and factor B. Again, because those means are different, the column and row means are different, but there's no interaction, again, because those lines are parallel in the graph. And then for the C down there, the data is showing no main effects for either one, but there is an interaction. So if you look, the column means are all the same, right? So it looks like there's no effect whatsoever. But if you look at the lines, and if you look internally at the cell means, they are different. And so obviously there is an interaction occurring. That's just kind of a great visual way to kind of remind you of what all of that looks like. All right, so our knowledge check really quickly. Which of the following is possible outcome for a 2x2 factorial design? Remember, 2x2 means there's two independent variables, two factors, because there's two numbers here. So that means that there's going to be two main effects, a main effect for each variable, and then a possible interaction. So that would be A, right? There's two independent variables, so two possible main effects and one possible interaction between the two variables. Okay, we'll get into the more complicated stuff in the next section, but let's do the learning check really quickly. So the following data represents the means for each treatment condition in a two-factor experiment. What pattern of results is shown in the data? So you can see here, if we do the means really quickly, because they don't calculate the means for us. So if we do 30 plus 20, that's 50, and 40 plus 10 is 50 as well. So that means the average is going to be 25 for both rows. Okay, so there's no main effect for B. Okay, now if we look at the columns, 30 to 40, there is 10, and 20 to 10, I'm sorry, I'm averaging, not doing the math. I'm not doing subtraction. 30 plus 40 is 70. So there's the average would be 35 for A1. And then for A2, 30 is what you add those together. So the average would be 15. So A1 is 35, A2 is 15. So the averages, the means are different from A1 to A2. So that means there is a main effect for factor A. So if we look down here at our answers, that rolls out the first two. So there's a main effect for factor A, so it's got to be one of the second two answers. So the difference between those two, if you want to look really quickly, is there interaction or is there a main effect for B? We need to find out. There says there's no main effect for factor B. We already figured that out. So we need to know if there's an interaction or not. So if you look, and this is what I was doing a second ago, I got ahead of myself. So the difference between 30 and 40 is 10, and between 20 and 10 is also 10. But if you look carefully, the direction is different. So from B1 to B2 in this column, we're increasing. So B2 scores were higher in the A1 column, but in the A2 column, the B2 score was lower than the B1. So the B1 condition was higher for A2. So because those are different directions, that means that there is an interaction happening. So our answer is that there's a main effect for A, an interaction, but there's no main effect for factor B. And then the results for a two-factor ANOVA show no main effect for factor A, but a significant interaction. What can you conclude based on this pattern of results? So there's no main effect for factor A, but there is an interaction. So hopefully that depends word jumped out at you and you realized that factor A may or may not have an effect, but if it does have an effect, it's going to depend on the levels of factor B, right? Because there was no main effect for factor A. So you can't say this top answer, factor A has no effect, because there was an interaction. So there had to be something going on with factor A. It's also not the third answer because we already showed that there was no main effect for factor A. So you can't say that it had to have an effect because there was no main effect. And then So the effect of factor A isn't going to be consistent, right? You're not going to always have an effect for that. It's going to depend on factor B. And then obviously the bottom answer is incorrect as well, because factor A is not constant across all levels of factor B, or there would be no interaction. The point is that it's different. And then which of the following is not a possible outcome for a 2x2 factorial design? So not possible. So again, 2x2 means two independent variables. So we're going to have two main effects. So that's the first two answers. And there could be an interaction or there could not be an interaction. So both of those are correct. And so this third one, no main effect for either but an interaction, that could be true as well, because you still have two main effects and an interaction. Those three things are possible. And so any of those three scenarios are possible for a 2x2 factorial design. So our answer is all of the above are possible outcomes. All right, so that is it for 11.2. And I know that was a lot of information. So if you guys have any questions about anything, please feel free to email me.